Okay, hello everyone. My name is Tom Langford. I am a research scientist here at the Center for Research Computing, currently obviously not at the center, but from my house. But I am excited and appreciate everyone joining us for this session on parallel programming with Python. So this is an area that I use pretty extensively in my research. I also work in the physics department doing particle physics, and so I use this type of toolkit quite frequently. And so I'm excited and happy to share it with you. A couple of technical notes. The first one is these slides are generated from a Jupyter notebook. In fact, I can exit the notebook and show you what that looks like. And this is currently being hosted and run from the cluster, from Grace in particular. The notebook will work on Grace, which is great. Additionally, the slides are saved and hosted on our website. So this is the link is posted by Christine, who is kind of manning the chat today. So feel free to grab those slides, and you can thumb through them. And additionally, there's a GitHub repository that I have a link to in just a second that you'll be able to actually download the whole notebook along with the ways to get set up and modules that you need, etc. So with that, I think we'll go ahead and get started. Kind of generally speaking, this tutorial is all written in Python 3. There are, in particular, I'm currently using Python 3.8, although there's not really a lot that's different between 3.6, 3.7, 3.8. So anything that's kind of a more recent Python 3 version, you should be just fine. I'm also using a collection of data modules, so pandas and NumPy, as well as matplotlib for doing some plotting. I'm using the multiprocessing module, which is what we're going to be using for a lot of the parallelism that is happening on local machines. And so we'll dive into some of that. There's an example that uses this PIL, this processing image. It's an image library, so we use that for some image processing. That says there's a typo in that. That's unfortunate. And then some of the more advanced parallelism, we use MPI for pi. And so we'll talk through that. Finally, the last module that we make use of is called QPy. And this is, or QPy, this is a tool that's a GPU accelerated version of NumPy that uses NVIDIA GPU. So if you are on a Mac, unfortunately that will not compile for you, but it will work just fine on Grace or on a Windows box if you have a GPU. And finally, as I said, everything in this is a Jupyter notebook. And then the slides are being generated from that. So that is good to go. Just a comment, Python 2 versus Python 3. Python 2 officially I won't say end of life, it's still being supported for security patches and things, but there are no new features. And it's time to put Python 2 to rest. It was a fantastic tool, and now we just need to move to Python 3. So there's a big discussion of this here on the Python wiki. There are a lot of really nice features that we'll use in this talk, as well as just in general, that use Python, that are only available in Python 3. So really worth transition. So as I mentioned, this is the GitHub repository, for this, this workshop. This QR code will also take you to this website. And you can download the zip file, or you can clone the repo, whatever you prefer, and get going with all the tools. Additionally, this is for the first half where we're not working on the GPU, you can launch an Amazon Web Service container that has everything pre-built and ready to go using AWS. And that's at that link. It gets you up through the first half. There are no GPUs available in these containers from my binder, so what can you do? But this is another option for trying some things out. So, right, so the actual talk that we're going to be going through today, we're going to touch and kind of begin with the foundation of parallel concepts. So what do I mean when I say parallel processing or parallel programming? And we're going to break it down to different classes of parallel problems, the types of problems that you might run into, and then how you might want to think about using parallel tools to solve them. We'll then focus, for this talk, we'll focus on Python-specific implementations of different types of parallel programming. There is another tutorial that's a parallel R that one of my colleagues from YCRC led, I think, last week. And so those slides are also available if you are an R programmer by default. It's another set of tools that you can look at. And then finally, we kind of will touch on tools for further exploration, things that I think are exciting and new that are worth spending some time on, but unfortunately don't fit in this talk. So parallel concepts. What do I mean by parallel? I think it's really helpful to say, to define what isn't parallel. So this is what is called serial execution. And typically when you're writing a program, the code is executed one line at a time in order. And so in this particular example, we're defining an array of numbers, 6 numbers, and then we're defining a function that returns the square of the input of that function. And then we make a little for loop that for every element in this array, we print out this function of that, the square of that element, and that gives us this nice list that goes up to 25. So everything happened here one line after another. And so this is serial execution. And in fact, there's a built-in way that Python and actually many languages provide. It's called a map function that does just what I had in that explanation. It's a tool that feels like I skipped something. No, sorry. Apologies. So this is a map function. What it does is it takes inputs, one input that is a function, the other that is an array of values, and then it does that for loop for us. And so in this case, it's just a wrapper for this. It appends, it has this output data structure, and then it loops over each element in the input array, applies the function to that element, and appends the output to this list. And so now we have this output data structure ready to go. And if we use this function on the bar function from before, that squaring function, we get this response. So this seems perfectly consistent with what we are expecting. And very helpfully, as I mentioned, there is a built-in tool. Python has quite an extensive standard library, so you don't have to roll your own version of a lot of these things. And so this is the Python map. So you take in the function, you take in the array of values, and this applies that function to these values and returns the results. So the built-in is much better than my kind of super basic code. So obviously the built-in is the one we should use, but this is basically what it's doing. I should pause and note that at any point, if there are questions, you should be able to raise your hand and we'll get a notification that there's a question. You can also post into the chat, and Christine is helping to man that. So please interrupt, raise your hand, ask a question as needed. This is much more effective when it's more of a back and forth. So, okay, so we've touched on serial and we've touched on the map function. And so what's really important to note is that in certain types of, when you're thinking about parallel programming, you have to often ask, how much does each step of what I'm trying to parallelize depend on the other steps? Do any of these steps need to know about what's happening in the other steps? And since in this particular example where we're having this map function on this array, there's no dependency between them. There's nothing that's waiting to say, oh, well, I need the output of earlier so that I can know what to do now. And so rather than looping over each value one after the other, we could just as easily create multiple instances of the function, apply that to each value at the same time, and then return all of the values at once. And so this is in broad terms, this is what multiprocessing does when using a pool of workers. We're going to talk into that. So multiprocessing is a really large module. Actually, it has a number of different ways to do parallelism, and it can do with threads that use the same process. It can do with separate processes. We're going to focus on one particular tool that I think is very flexible and very easy to somewhat grasp, and this is called the pool. So this creates a pool of workers that are all independent processes that are then available to be workers to take in whatever inputs and return whatever outputs. And it has a version of that map function that then applies the function to the pool of workers and then returns the results. So this is really handy, and so we're going to use this as our test bed for this work. So the way that this works is we have to import the module, and we create a pool of workers. And in this case, we're creating 6 different workers. So this is 6 independent processes that are being spawned by the single parent process. And we're going to call that pool. And we're going to use the method that's built into that to map our function. In this case, I'm just using NumPy's square function rather than my own. It doesn't really matter. And we're going to map this function onto that same array as before. But this time, we're going to do it using the pool of workers rather than just using the standard library map. And when you run that, you actually find that, in fact, you get, not surprisingly at all, you get the same result. So this is a somewhat trivial example, and so I think it's really helpful to dive a little bit more into how this is working with a toy problem. So we're going to create a new function, and this function is called parallel test. And all it does is it takes whatever the input is, it prints that out. So it just takes the input and prints it out. But it also prints out the process ID number. That is the PID on the computer that says what process is currently being run. So this is going to be our tester function, so we can kind of see what's going on a little bit. So we can use this function, if we go back, so we can use parallel test, and we can map it onto that foo array, that array of 6 numbers, and see what it does. So first we're going to do it with the built-in map function. And so if we take map of parallel test on that array, you see that we print out the numbers 0 to 5, not a surprise, but we print out the PID, and it's the exact same for each step. And that's because this map is just like a loop. It's just taking one, then it does the next, then it does the next, then it does the next. So they all come out in order, as expected, but all with the same process ID number. However, if we do this with the multiprocessing module, with our pool of workers, so it's the exact same thing as we had before, a couple of things are different. And in particular, the first is the values do not get returned in order. Because we have created these independent workers, all 6 of them, and we give them the numbers, and then they return them whenever they're done, there's no guarantee that the order of these operations is going to be preserved. It's whomever comes back first. So that's one important difference. And the other is that each of these steps is being handled by a different process ID number. And so this is real parallelism. This is independent processes are running this function in parallel. And so with basically 2 lines, we've been able to parallelize a simple test. That's kind of nice. And it's one of the nice things about Python is that so much of it is some batteries included, as it were. Okay, so map is a really versatile function or method to take an input function. Whoops, that's not what I meant to do. To take an input function and apply it to each item in an array or a generator or any iterator actually. And in normal serial processing, this works just like a for loop, but it's a for loop you don't have to program, so that's kind of nice. But in parallel execution, this actually can set up these independent workers that can act completely independently and simultaneously to analyze or to do whatever is in that function and then return the results. So now we're going to take kind of a step into the different classes of parallelism. But first, are there any questions so far? It's all pretty basic so far. But yeah, is that someone is saying no? Excellent. Okay. Then we're going to dive into embarrassingly parallel problems. So this is a class of problems that is somewhat, I won't say pejoratively named this, but it's somewhat where it's easy to split them apart and it's easy to get near linear improvement in speed, which is really nice. So what do I mean by this? So many problems can be converted using multiprocessing that when they fall into the case of no subset needs to talk or know anything about the other processes that are happening. And so one such example is Monte Carlo type simulation. So I don't know if, let's see, is anyone in the chat familiar with this type of simulations, Monte Carlo type random number generators? I'm not seeing any hands, but okay. So the idea is that this uses random number generators to, in this case, we're going to calculate pi. And so we're going to calculate pi using random numbers. And the key is that we're going to change the random number generator's seed. So this is, we are not actually very good at programming true randomness. And so you have to actually seed your random number generator to say this is basically not quite this is where you begin, but it's kind of, it sets up the string of random numbers. And helpfully, if you use the same seed each time, you get the exact same set of random numbers that come after, which is great for reproducibility if you're trying to do some studies, but not great if you're trying to actually build up statistics of whatever you're simulating. But so in this example, we're going to define a function that calculates pi using random numbers, and then we're going to map that function onto an array of random seeds and try to boost the throughput with parallelism. So this is our function. And so in this function, it takes a single input, that's the random seed, and then, amusingly, it looks as though someone says that you've lost my presentation. Can people still see my slides? No, yes. That's strange. Huh, okay. Most people, it seems, can still see it, but some cannot. Strange. Okay. I'm going to keep going, and if the situation gets worse, we'll pause and do some yeah. I don't know what's going on. Okay. So this takes a random number generator using this random.random, and it then calculates pi. And the way it calculates pi is actually very simple. It draws a radius of a circle, and anything inside that radius counts towards pi, anything outside the radius doesn't. And then we use the area of the circle to tell us how to, what pi is. So it's a very simple, very classic way to do, to calculate pi. And so in this case, it's generating 1 million random numbers. And then we can run this in serial. So we can run with a single random number, with a single random number seed. And it takes about 300 milliseconds to run. So this particular example throughout the slides, I use the timeit module in Python. This is a really handy, what's called a magic function that you can put in your Jupyter Notebook cells, and it will, in this case, with a single percent sign, it just times the single line. Sometimes I'll use it with 2, and then it does the whole cell. So it's really handy. But so it prints out the average time it takes to run that particular command. And in this case, it took about 300 milliseconds. So we can make a list of our seeds. So if we want to have multiple seeds so that we can run these simulations in parallel and get different numbers, then here's our seed array. And when we run this serial version, we see that it's basically exactly 4 times as long, which is what we expect, right? It's just doing one followed by the other, followed by the other. So this is a perfectly natural way, this is the scaling we expect. However, if we use multiprocessing, we can actually reduce that throughput back down to nearly the same speed as a single stage of this. So this is doing 4 independent simulations, running them in parallel, returning the results, and then those results can be combined by us. In this case, it would be, we'd have to average the calculation of pi for each of the sub processes, and then we would have our better measure of pi. And it's not exactly equal to the single case, because there is some overhead. There is some cost to starting up the pool of workers, sending the functions to each of them, and compiling the results. So it's not free, but it's really close. And depending on how much setup time is required for the functions that you're using, it can be very efficient. So this is an example of very straightforward parallelism that can, significantly, in this situation, right, it's 300 milliseconds, who really cares? But if this was an hour for each step, and you're talking about it, running the difference between over lunch, the difference of it running the whole afternoon, that's an impactful to change. Similarly, if you could speed this up or put it to more processes, so my laptop only has maybe something like 8 threads that are possible. But if you were running on some workstation or on a bigger system, you could put this out to 20 and you could have significant throughput. So this is a really powerful tool with very little work on your end to set up. So another example of how this is really handy, and this is one that, again, this particular one comes up a lot in my type of work, where I have a lot of data files or input files, and I want to perform the same set of analysis or processing on those files. And so for, as a particle physicist, this might be data that's coming out of my experiment, and these, it's chunks of time, so it might be an hour's worth of data, and we might have 1,000 of these hours worth of data that we want to process. And we're doing the exact same actions on all of them, and there's no communication between the individual steps. That can be trivially parallelized. And so in this example, we're going to do some image processing, but it doesn't matter what the input file is, doesn't matter what the actions are, so long as it's independent of each other, it can be parallelized super efficiently. So in this case, we're going to define a function, takes an input file, performs some actions, and then returns an output file. And we're going to map that function on a list of a bunch of inputs. So we're going to use the Pillow, the PIL library, to do this, just because it's fun to have a little bit of a different type of example. And here is one of the input images that we're going to be playing with. So in this case, I have a collection of photos of train stations. This one is King's Cross, which is in London. And so if I just open the image and then I can display it, you see this very beautiful dome-type ceiling at King's Cross Station. And we can rotate that image by 180 degrees using this method, and it returns our output. So that's super easy and very trivial. And so let's actually just define a function that takes the input file, opens it, rotates it 180 degrees, and then saves it as a different file format. And so that's what this function does. We've called it image flipper. We have a file name. And I like to, since we're going to be saving this as a different file, I want to base our output file name on the input file name. So in this case, I have the base name, which is just the file name, stripping off the dot extension. I think each of these are, if I can go back a slide, these are all JPEGs. So we're going to strip off the JPEG extension. We're going to open the file. We're going to flip it by 180 degrees, and we're going to save it as a PDF. And so this is a really simple script. It does almost nothing that's fancy. But I have a list of about 12 or so different images. Again, this could be 10, 12, it could be 10,000. It's, this is a very flexible way to define some parallelism. So in this case, I just have a bunch of photos. And I'm going to create my pool of workers just as we did before. In this case, I'm defining it with 4 processes. Now, it's important to note the number of processes do not need to match the number of files or the number of inputs. It just is limiting the amount of parallelism. So in this case, this pool of workers, there are 4 workers, and it's going to start, this map is going to take the first 4, and it's going to throw them to the pool of workers. And then as they are returning their results, multiprocessing is going to start giving the next one. So the first, Victoria finishes first, it's going to be given Houston as the next task to do. And so the processes does not need to match the list or the length of the inputs, which is great because often we have, again, hundreds of inputs and we might only have 4 processes. So Stephen Gaffney has a question. Is os.path.basename better? 100%. I was just being lazy. So yes, there are much better ways to do some of this. For sometimes it's nice to be, to be a little lazy. But yes, os.path.basename, always a better solution. Okay. So from then you can apply this function onto this list, and what it does is it creates this whole set of PDFs with a new file name and with this underscore flipped. And if we were to open any of these, we would just see the image rotated upside down. And I can do that if people are interested. I think that's pretty easy, but well, it's fine. But the moral is that fairly trivially, we can take a bunch of input files, we can perform an action on each of them separately, and then produce a bunch of output files. And that is a generically useful workflow that applies to many, many different types of work. How do we determine the number of processes available on a given machine? So that's a very good question, Jeff. Typically, I'll break down this into 2 different types of systems. So when you are working on a system that is your system, so a workstation or a laptop, where you have access to the entire machine, you can typically just look at the number of cores that are available. And so this can be done, if it's a Mac, you can look at the system info, or you can look at the activity monitor. If it's a Windows box, I think there's something within the system monitor as well. Linux, you can look at top or htop to show that. And it's often good to not use every core that's available, because depending on how process intensive these are, how CPU intensive these tasks are, it can kind of gum up the machine and slow things down. So in general, I take, it's a bit of a guess, but you remove 1 or 2 cores from the total that have available, so you have some room to do other work while things are running. Now, if it's on a shared machine, you have to be careful that you don't start locking up other people's systems, right? So if this is a, oh, excuse me. If this is a shared workstation where there aren't controls that are put in place to limit how much processing you can do at a time, you want to be careful not to just gun up the whole machine. Similarly, on the cluster, if we start taking this, and we'll go to the cluster in a couple of examples, but this would be equivalent to the number of CPUs that you request from the cluster, and so there are ways that you can actually make this a variable. So on the cluster, when you request 4 CPUs from Slurm, in one of the environment variables that's generated is the number of CPUs. And so you can use that for this so that you have something that's flexible. So if one day you request 10, you can have it be 10. But if the next day you only request 4, it dynamically changes. So that's a pretty straightforward thing to do. Okay. Right. So we've got our set of PDF files with our new names and our new images. So let's talk, actually, this is a good segue. Let's talk about how to do embarrassingly parallel processing on the clusters. So this is a little bit different than doing it on your local machine for a couple of reasons. And the main reason is that, in fact, the clusters already have a tool that's managing parallel processing that's called Slurm. This is the scheduler that actually decides where it can run various jobs. And whereas on my local laptop or on a workstation in my lab, I have to manage the parallelism using multiprocessing or things like that. On the cluster, for this type of problem, for these trivially parallelized problems, you don't have to do that. And in fact, there's a nice wrapper for submitting these types of jobs to Slurm that we've written that's called Dead Simple Queue. And so I'm going to talk about how we can actually use Dead Simple Queue, or DSQ, as I'll probably call it, which is a module that's available on all of our clusters so that you can submit these types of jobs very, very simply. So what is DSQ? So this is very, very similar to the map functionality that we touched on earlier. And you can load it. This is a typo. I'm just going to delete that right now. That's no longer the case. So you can load it like this, module load DSQ. And this is a tool to help us create job arrays. And so these are arrays of similar jobs that are spawned wherever on the cluster it works. So this is the docs, the beginning of the help file for it. I'm not going to read this. This is mostly for people offline. But the idea is very, very similar to a map. So it creates a list of jobs, and this can be a single function. It can be slightly different functions. It can actually be multiple steps. But we're going to leverage Slurm to do the divvying up of these jobs and figuring out where to run them. And what's really, really powerful about this is that Slurm knows how to run jobs across the entire cluster, whereas multiprocessing only knows how to run jobs on a single local or a single machine. So if you were going to try to do multiprocessing and you requested 10 CPUs from Slurm and you wanted to divvy up the jobs, multiprocessing can only fit on a single node because it doesn't know how to communicate between nodes. Slurm does know how to communicate between nodes. And so that level of abstraction, you don't have to deal with it. Slurm can do all of this complicated between node setup. So you can run many, many more jobs at once, hundreds, rather than the kind of dozen that you could run on a single node. And it can be much more flexible. So the key to this is what is called a job file. And so I'm going to talk about how to create a job file and then how to actually submit this job to the cluster. So this is more of the docs for DSQ. So we're not going to get too much into it. That's for later reading. But so we're going to do that image flipping example from before. But in this case, we're going to create it as a script. So we're going to have a file that's called imageflipper.py, and it's a standalone script. So it imports the various tools that we need, and it gets the argument, so a command line argument, in this case argv, argv of 0 is the name of the function, and then argv of 1 is the name of whatever argument is passed to it. This is a very, very simple way to do arguments, command line arguments. There are much more sophisticated ways that use specific libraries like argparse or optparse. Once you get into more complicated things, that's helpful. This is just a bare bones way to do it. So we get the command line argument that's going to be our input file name. Not what I meant to do. We're going to do that same business of extracting the base name. We're going to open the file, rotate it by 180 degrees, and then save the output. So this is exactly the same thing that we had defined as a function before, but now I've just made it a script. And now we have to actually tell Slurm what jobs we want to do. And this is done in the following syntax. So DSQ, dead simple Q, takes each line as an individual independent job that it wants to run. And so in this case, each line here is, we're going to take Python, our file, our script, imageflipper.py, and then the data file that is being passed to it. And so this is just me printing it out to screen. We could just as easily have saved this to a text file. However we get it into a text file is somewhat up to us. Honestly, you could just type it. But this is an easier way to make sure there are no typos. So you would copy this, paste it into a text file, or save it as an output text file, whichever is your preference. But this is now the list of independent jobs that we want Slurm to run. If there were multiple stages, for instance, if we had a script that was image flipper, and then maybe we wanted to take the output of this function and do a next step of analysis to it, we could put a semicolon here, and it would be, and then it would be stage 2, Python stage 2.py, and then the file. And that way, everything that is needed for this job, the dependencies are managed. So you can string together multiple steps with semicolons, but this relies on a new line being the distinguishing between the independent jobs. And then we can call DSQ with this text file, this jf.txt is what we saved it as, and it generates for us the Slurm submission script, which is quite nice. So in this case, this is what we run from the command line, and then this is what is actually saved to file. So this is saved into a text file, a Slurm S-batch submission script that we can submit however we like. And it populates a bunch of the default values. So in particular, it's populating that there's 1 CPU for each. It's also populating that there are 10 different lines in that file. And so that is now what needs to be, this is how Slurm is setting up the job. So then we can either, we can also pass for it a bunch of the Slurm commands. So if we want to run this on the day partition, if we think it's going to take 6 hours and need 10 gigabytes per CPU, that's fine. We can pass all of those parameters to DSQ in this fashion. And if we use the -- submit flag, it will just submit the job directly to the cluster. So it doesn't even need to generate that separate S-batch submission script. But this is really quite handy because it gives us a way to, rather than having some for loop where we submit a bunch of different jobs or manually doing it, we can actually submit a whole array of jobs all at once that Slurm knows how to parallelize. So actually, go back. I want to pause here and also note that this does a lot of really nice things, not just for the users, but also for the admins of the clusters. Slurm has to, for every job that is submitted to the cluster, there is some overhead for actually starting and stopping that job. And Slurm has to ask each job what are the requirements of this particular job, what are the requirements of the next job, and so forth. And that can actually add up to some of the time it takes for jobs to launch. Job arrays are special in that no matter how long the job array is, in this example it was 10, but it could just as easily have been 1,000 or 10,000. Slurm only has to ask once, what are the things required to run any of these jobs? And that's very powerful because it means that Slurm can be much more efficient to manage those jobs. So the jobs get scheduled faster, so everyone's jobs work better. And you don't have to have independent or different job ID numbers for each of your 10,000 separate jobs. They're all given a single job ID with an underscore and then the array ID. And that makes bookkeeping much, much easier. So DSQ is really great. Job arrays are really great. And it looks like there is a question. I'm sorry for not seeing this earlier. So Stephen asks, is there a good or recommended way for a Python script to tell when a Slurm job is complete? That's an interesting question. Slurm will report when jobs are done. System call squeak, to SQ. Yeah, so I would avoid programmatic calls to SQ. And I'll say for the following reason. Every time that you ping SQ, it's a database query that has to get reported back. And it can, if you have that in a for loop, or you're checking it frequently, it can actually be a shockingly taxing thing for the cluster to do. A much easier way would be for in your job, for part of the last step in that job would be, for instance, to create a lock file or create or remove a lock file. So that's one way where you just kind of create an empty file, and then you have something else that's checking for the existence of that file. That's one option. Another is, I think that's the easiest that I can think of at the moment. And then you have this Python script that's running and checking whether that file exists. And file system calls are much, much more efficient than SQ calls. So that would be a recommendation, but it really depends on the task and what's happening. So another is to actually, one of the slides that I skipped, if we go back up here, DSQ, part of its work is that it creates this output file as it goes. So as jobs finish, this is getting populated with the individual outputs from each subjob. So in this particular case, we'll have the job ID, the exit code. If it finished successfully, it'll get a 0. If it finished if it's non-zero, it's generally an error. The time started, the time stopped, the total elapsed time, and the actual job that was run. So this is a very helpful file. So if you're using DSQ, you can just watch this file and see what's happening. So either with tail or with a Python script itself. If you're not using DSQ, it's a little bit more complicated. Does that answer your question, Stephen? Excellent. All right. So it is about 1:50. So we're going to get into not so embarrassingly parallel problems, but I want to pause. There's another question. Excellent. Yes, from Cheng Luo. Regarding the multiprocessing module, what if I want to save the results calculated by different processes into a global shared variable? Yeah, so this is, so if we go back, actually, let's go back to where we're talking about multiprocessing. And so it's easiest right here. So this is back to our Monte Carlo calculation of pi. So if we look, actually, I'm going to, I think this will work. This is a live notebook, so I'm pretty sure that this will work, but nothing quite like doing things on the fly. Okay, so this map actually returns a list of the individual results. So in this case, PyMC, our function, if we go back to where that function is defined, this returns its own little counter of pi. So this is going to return the fraction of values that are inside the radius, and from that you can calculate pi. And so this map returns that value as a list. So result here is a list of 4, since there are 4 processes, or rather the 4 since there are 4 seeds in my seed array. It is 4 independent calculations of pi. So in multiprocessing, it spawns the individual workers, then those workers return their results, and then you can do stuff with that result. So this is exactly what you're looking for. The challenge is, if you want to scale things up bigger beyond what multiprocessing can do, you need to come up with a different way to report the values back. And often the easiest way to do that is to just save it to disk. And so, especially if it's something where you have a specific value that's being calculated or some sort of output that's natural, instead of returning those back and then doing stuff, you can save them to disk with a unique file name. And then you have a second strip or a second function that takes all of those output files and pulls them together. I remember there is some module like manager. I'm not familiar with manager. It's not to say that it doesn't exist. There's quite a bit of Python that I'm not familiar with. Okay, within multiprocessing. So it very well could exist. Map kind of gives it to you for free, right? So let me just, pretty sure, no, that's a different one. So let's see. If I take PyMC of 1, it's returning pi. And in fact, I just noticed, well, so if I do this line, yeah, I think you're right, Steven. So let me just take this line and just paste it here. In this case, here are the 4 separate versions of pi that are being calculated. So let's see what multiprocessing does. It's worth looking into. I apologize, it's not a tool that I have used so far, but there are, Python aims to be a system that has what I'll say, one right way to do something, but it wholly misses that goal. There are many, many ways to do almost everything in Python, and so this is not so different. But yeah, so but this is really simple. But again, it's limited to a single workstation or a single node on the cluster. And if you want to start doing things that are bigger, if you want to run hundreds of jobs at once, you really want to start thinking about how can you split jobs up that utilize the file system. And in particular, we'll have an output file and then a second round of processing that waits for all of those to finish, that then aggregates the output files and does stuff with it. So that's a really, when thinking about the style of moving things from a local workstation where you have to manage the parallelism to the cluster where we can leverage Slurm to do it much more efficiently than we are. So with that, before we get into MPI for Pi and GPU-based things, I think we should take a 5-minute break. I need to drink some water so I don't go hoarse. And so let's reconvene at 2 o'clock. I'll leave this, the room will stay open. I'm just gonna kill my camera so I can get something to drink. And then we'll pick back up with MPI for Pi and GPUs in just a bit. Okay, so we're gonna go ahead and get started again. All right, so are there any questions about DSQ or the more embarrassingly parallel problems before we dive into the not so embarrassing parallel problems? All right, then with that, I will say let's get going. So everything that we've talked about so far has relied upon things not needing to communicate between independent processes. There are lots of problems where that's the case, those data processing, Monte Carlo simulations, that sort of thing. But there are a lot of problems where that's not the case. Some examples are things where you're trying to, for instance, galaxy formation, where you have a big 3-dimensional volume and everything depends on its interactions with every other thing. Same thing with electric field simulations, analysis of a single large data set, something with a really big data frame or a big n-dimensional matrix, or things that are doing search and sort algorithms. So lots of these things are not embarrassingly parallel, but could still benefit from some speed up. And so we want to think about how we can do that. And so there is a standard protocol for sending communications between processes. And this is called MPI. And in particular, this is designed for sending communication even when it's not on the same node or not on the same computer. And so this this is incredibly powerful. And there is a Python implementation of this called MPI for Pi. This is a link to the docs page. Feel free to go into it. But the key is that this is a point-to-point, so send and receive type communication, or collective, which are kind of broadcasts and scatters and gathers, communications of any Python object that you can pickle. So dictionaries, lists, sets, that sort of thing. And there are also optimized communicators for things like NumPy arrays that are more, that are a little bit more easy to know what's coming. And so we're going to go through a few examples of how you can do this with some simple MPI examples. I will pause to note that while there are many tools that can be made faster with certain types of programming like this, there are often many ways to solve these puzzles, and MPI is a particularly complicated one that I won't caution against it, but it can be really challenging. So we're going to dive into it, and then after this, we're going to talk about some GPU stuff that I think is really fun and exciting. Okay, so it's helpful to have some definitions before we get going. So these are standard terms that are used in MPI, regardless of which flavor of MPI you're using. If you're using MPI based just in C, C++, or in Python, these are basically the same terms. So the first one is the COM, and this is the communication world that's defined by MPI. So when it's setting up the communication, it is doing so with individual nodes or processes scattered across kind of either a local machine or multiple machines. Each of these members is given a rank, and that rank is an ID number that's given to all of the members of this communication, and it's how things can communicate with each other. The size is the total number of those members, And as I mentioned before, we have these send and receive, which is a one-to-one communication. You can send a value, you can receive a value. But you can also have one-to-many communication, which is called a broadcast. So this might be, I have a single process that wants to send out a signal to all other processes at the same time. That's a broadcast. A scatter is different in that this is a way to chunk data. So it might take one really long array and split it into individual pieces and send one piece to one process, one piece to a different process, and so forth. And it uses the rank as how to do that. And then finally, the kind of the inverse problem of a scatter is a gather. And so the gather allows a single rank to collect different values from all the other ranks. So we're going to talk about each of these, but this is important to have up front. So helpfully, you can install MPI for Pi using Conda. So on the clusters, there is mini Conda, and this again is slightly out of date, so I apologize for that. I'm just going to fix it on the fly. And we are using 3.8 at the moment, so we'll be doing that. And so in this case, we can create a Conda environment called MPI, and we're going to specify that we want Python, MPI for Pi, NumPy, and SciPy. And these are just a collection of modules. And then we can do this either on your local machine with this command, or just the same on the cluster once you've loaded the mini Conda module. And so the simplest example of an MPI program is one that all it does is it reports the rank of the various processes. So all of these, by the way, these mpi.simple.py, these are scripts that are included in the GitHub repository and are there for you to look at and riff on. So when I reference a file name, I think all of them exist within the GitHub repository. And if not, that's a mistake and I'll fix it. But so in this case, we're going to load the MPI module. We're going to set up a communication world. And then we're going to get the size of that world. And then we're going to get the rank of each of these. And then finally, we're going to print out these things. So we're going to print out what the rank is. We're going to print out.
Do you have a breakdown? I think he has a fever.
I'm really sorry. I'm going to ask everyone to just pause for just a moment. I will be right back. I apologize. Okay, MPI. This is where we were a moment ago. So, so this is a very simple program. All it does is it sets up the COM world, it gets the size and the rank, and then finally it gets the PID, the process ID number, and it prints those things out. And so if we run this, we don't just run it with Python mpi.simple.py. You have to pass it through the MPI run wrapper. And so this is the way that you set this up. And in this example, we're telling it that we want there to be 4 members of the COM world. So in this case, this is how you run that command. And when you run it, it outputs the following. So rank 0 has PID blah, and so forth. Again, there are 4 lines, one for each of the ranks. They all have separate process ID numbers. Okay, so again, MPI run is the wrapper for the MPI interface. The -n is saying how many workers to create it with. And then finally, we're saying, this is what we want to run inside that MPI COM world. And it's going to run it on each of the 4 workers separately. So that's a really obviously simple explanation or simple setup. But we also have the ability to send and receive messages and data between individual workers. And with a note that this can be a little tricky because these are what are called blocking commands. So if I have a receive statement or a send statement, but the receive statement's the particular one, it will wait until it receives the data. And so if you have programmed it not correctly, it will not ever receive the data, and it will just sit there and say, I was told I should receive some data, and I'm not moving on until I do. And so that is one of the most challenging parts of MPI, is managing these blocking commands. So in this case, we have a com.send. So we're going to send an object to a destination. And we can give it tags that can be used for filters. This can say what kind of data, what kind of setup it is. But this is optional. Similarly, on the other side, to receive it, we can say where we want to receive it from. This can be a specific rank, or it can be any source. So this is the generic syntax. So let's actually see how this is used. So we're going to do a MPI communication world again. So this is a file that lives in the GitHub repository. And in this example, let me zoom out just a little bit. Try to, no, it's not going to give me more. Okay, fine. So we're going to, same as before, we're going to set up the com world. We're going to get the size and the rank of each individual worker. And this is the part that can get challenging. You have to think about, this program is going to be run on each separate rank. And you have to tell the program how to behave if you're on specific ranks. So in this case, if the rank of this particular setup is 0, I create a message, and then I want to send it to rank 1. So rank 0's job is going to send a message over to rank 1. Similarly, rank 1 is going to receive, it's waiting to receive a message, and then it's going to print that message along with its own rank. So let's actually run that. And if you do the same MPI run as we've done before, it prints out rank 1 hello world. And so that is a message that was sent from rank 0. Rank 1 did not know what that message was until it received it. So that's kind of neat. So rank 0 sends the message, rank 1 receives it. And in this case, since I had 4 workers, the other 2 workers are just bystanding, so not doing anything in this example. Let's do an example where they actually do stuff. So this is a broadcast example. So this is a little bit more complicated. And so we'll walk through this again. So actually, the notebook interface, not always the perfect interface. But okay, so we're importing MPI, defining the com world, that is all the same. But now we're going to create some data. We're going to create the data on rank 0. And so in this case, data is a dictionary with 2 values, or two keys. Key 1, is this list. And key 2 is a tuple of strings. So this is a mixed data type dictionary, but it is something that is pickable, so it can be passed between using MPI. Importantly, on rank 0, we define it to mean something, but everywhere else, data is being defined, but is set to none. So that's going to act as kind of a holder or a placeholder for the data that A will receive. So we're going to broadcast that data. So data gets broadcast from rank 0. So the root, the origin of these data are rank 0. So it's going to send out this set of information. And then each rank is going to append to key 1 the value of its own rank. So this is just a way to get unique data that's across all of the different workers. And then it's going to print the result. So it's going to print the rank and the data. And so we're going to run this, and this again is MPI message. And what we get is rank 0, 2, 3, 1, not in order again. It's any order, it's whatever finishes first. And each of these now has their own rank that have been appended to this list. So we've taken data that originated on rank 0, we've propagated it to all ranks, and then we've modified those data and reported them back. So this is getting at the guts of how you might start doing various types of complicated parallelism. So let's actually do a data analysis with this. So we've got our boilerplate, but this time we're going to import NumPy. And we want to create a large array of data on rank 0. And in this case, it's 100 million values. And they're going to be a randomly distributed set of numbers. So it's 100 million random values that are centered at the number 10 with a sigma of 5 and size of num data, so 100 million. So this is a really big list. Or I'm sorry, a really big array. But it only gets created on rank 0. We then want to create a data structure that is a container for part of that big data. And in this case, we're going to create an empty array that is the length of what we started with, this 100 million, divided by the number of workers in our common world. So if we have 10 workers, this will be 10 million. If we have 5 workers, it'll be 20 million, that sort of thing. So it's a dynamically scalable problem. And we're saying that the data type is a double. So this is looking a little bit more like C or C++, where we have to really specify data types and manage things. We're going to then scatter our data. So this is the command that takes a single data structure, and it scatters it from root 0, where this data is actually, where this data is this list of array, or this array of numbers. And it's going to populate the partial arrays that are located on all the different workers. And then so that's a scatter. And then on rank 0, we want to create another container that is the empty data structure for where we want to receive those some computed values. And in this case, we're going to average this big list. And so then we want to gather the results. So in each rank is going to average its own chunk of the data. It's then going to send it back to rank 0, and it's going to populate the reduced, the array named reduced. And then we're going to take the average of that, which is our result. So we start with 100 million values, we split it into chunks, we send those chunks out to all the different workers where they get averaged independently in parallel. They get sent back kind of the sub result. So each of them is going to send back some number. And then we want to get the full reduction by taking the average of that set of averages. Okay. This is a totally contrived example, but it's a way to conceptualize how we might want to split data to then do certain procedures on it and then return back results. So in this case, the only thing that's going to print is if you're rank 0. So rank 0 is going to print the output. And shockingly, it gets very, very close to 10. So we started with numbers that were randomly generated around 10, and we get back an average of those numbers that's very, very close to 10. And you could calculate, is it as close to 10 as it should be? And it is. It's not a very interesting example, other than the mechanism is quite powerful. We start with a big chunk of data on one rank, we scatter it out, each worker does part of the analysis in parallel, they all send it back to the main worker, and then the result is compiled. So this is somewhat actually getting to I think it was to Chung's question about getting back results from the individual workers. This is doing it for in a much more complicated way than multiprocessing, but it's a similar effect. So MPI is incredibly powerful. The repository for this course includes a number of example files that you are free to take and to modify and tweak and play with. And this MPI for Pi tool is kind of, I think, is one of the more friendly MPI implementations. But it is incredibly powerful. And it's, this is just some toys. To actually start doing things, you can do some really powerful things. And in particular, the things that I think are most powerful are when you have communications between adjacent ranks. So if the we go back to the messaging, so if we want to send, if instead of root equals 0, it could be root equals my rank minus 1. So it could be, I wait for the rank just before me to send my value. And then I send mine to the next and to the next. And so you can create a ring of processes that are all sending messages to each other. It's very neat, it's very powerful. It can be very complicated to visualize and to make sure that you are really kind of grasping what's going on. At least it is for me. But this is a powerful tool. So the last piece of our talk today is about what I think is one of the most interesting areas of parallel programming that are that's being focused on right now, and that's using accelerators, and in particular GPUs, so graphical processing units. Before we dive into that, are there questions about MPI that we should answer before going, or should we dive into GPUs? Okay. Was the D-type specification necessary in the last example? Let's go back. So this is exactly what Stephen is asking about. I believe, so I'm reasonably sure there is a default data type. Since we're passing a NumPy array, I think we want to be careful. There's something I kind of glossed over. I mentioned, of course, that there were these optimized communicators for NumPy arrays. This was at the beginning here. Yeah, so the send and receive, broadcast, scatter, gather, all of that, but as well as these optimized communicators. The optimized ones have capital letters that begin them, which is a totally subtle and not nearly as clear as I think it should be for how you specify this is, send with a little s is an any pickable object. Send with a capital S is saying this is a NumPy type object. This is something that has a data type, and it knows how to set up the memory for it. So when we do little s, that's when it's sending some generic thing. But when we were doing here in the scatter, this is a capital S, and that is this optimized thing for NumPy. So in this case, yes, I believe you do need the data type. If we were not doing the capital S, this optimized NumPy communication, I think you don't. But it's this is, there's a lot of subtlety, and there's also, frankly, there's a lot of optimization that you can go into to try to get more performance out of this. Speed up the data, the communication, speed up the allocation, use as little memory as necessary, that sort of thing. This is all tied into that. So if I was only sending integers, I wouldn't be specifying a double because it would be wasting memory depending on the scale of integers. That sort of thing. Okay. Okay. Then with that, let's jump into GPUs. So I think it's important again, to note to define it based on what it's not. So everything we've been doing so far to this point, and actually most of computing, frankly, for a long time, has been using the CPU, the central processing unit. These are very, very flexible computing elements. They typically have a few cores. My laptop has 4, but they're very fast with large amounts of slow access RAM. but they're capable of doing any task that it's given to it. So they're super flexible. Recently, I'll say in the last 20 years, 10, 20 years, there's been a growth of dedicated hardware that are designed to do a very small subset of tasks. It actually started with image and processing graphics. These GPUs are developed to handle specific tasks, ray tracing, image rendering, that sort of thing. And they typically have thousands of cores or hundreds of cores with small but very fast memory. And this is a combination that's kind of the exact, I won't say the opposite of CPUs, but they're dedicated hardware that's designed to do certain types of tasks. You cannot do any task you like on a GPU. It has to be certain types of things, and you have to program for it with that in mind. However, tasks that can be split across GPU cores can be incredibly accelerated and made much, much faster. And it turns out that there's a lot of data processing, matrix manipulation, data massaging that can happen with these optimized systems for really quite ridiculous levels of speed up. So we're going to touch base on that in this. There we go. Okay. And many of these are what we call vectorized functions. These are things that you're applying the same function to every element of an array. So that's, it's similar to how we're talking about doing a map. Those map functions, that's a very similar conceptual to what we mean by vectorized. For example, most NumPy operations, the mean, inverting matrix, that sort of thing, those things are all vectorized, so they go much faster. Another example is matrix multiplication with large matrices, so 10,000 by 10,000 type matrices. So there's a lot of interesting ways that you can do vectorized function, but you have to think about things differently. For loops, not vectorized. That's kind of the hopefully, my laptop does not have a GPU in it. Neither does the desktop that's sitting at my desk. But both actually, I think now at this point, I think every cluster has GPUs in it. Certainly Grace and Farnham do, but I believe also now Milgram and Ruddle, depending on where people work, have GPUs available. These are all NVIDIA GPUs that use CUDA. So CUDA is the programming language that you can use to tap into, to use them for computing. So you can request these GPUs, and there are two public GPU partitions that that are commons that everyone has access to. One is called GPU devel. And this has shorter wall times, fewer nodes, but the goal is you should be able to demo and work through kinks on that particular system, and then you can deploy it to larger systems that are on just the GPU partition. These GPUs are what are called general resources, or GRES. And so to request a GPU, you need to add this flag that's GRES equals GPU:1. And in this case, it's asking for a single GPU. If this colon was :2, it would ask for 2. You can also specify specific types of GPUs. On Grace, there are 5 or 6 different types of GPUs that are available, different ages, different amounts of memory, that sort of thing. And so in the middle, you can add another statement. It would be GPU:P100:1, something like that. And there's a lot on our documentation page about how to do this. Once you have done that, you have been given access on whatever particular node you have for that GPU. There are a number of toolkits within Python to actually start working with these GPUs. There is a Python implementation of CUDA. I do not necessarily recommend everyone start off by looking at CUDA. It's really complicated. This is very powerful. It gives you the ability to write your own tools in Python that interface directly with CUDA. But it's still quite complicated, but it's very powerful. Helpfully, over the last year or two, there's been a real push to create another layer of abstraction on top of that. And actually, much of the work has actually been done by NVIDIA. So QP, which is this NumPy, GPU accelerated NumPy that I mentioned at the beginning, is one such thing. There's also QDF, which is for data frames. And a lot of these are kind of under the kind of the header of Rapids. Rapids is a toolkit that's being developed by NVIDIA. It's all in Python. It's aimed at GPU accelerated data science. So really, the drivers of this particular field are data science that as people are trying to use more and more GPUs. I'm going to do some examples with QP, or QPy. I have no idea the right way to pronounce that. Rapids and QDF and QML, which is their GPU accelerated machine learning, these are things that are incredibly powerful, and they're very new. So they're being actively worked on quite a bit. So, so I'm going to focus on the NumPy replacement since we've done a lot of NumPy so far, but the pandas replacement data QDF is also exceptional. Okay. So to get started, you load the module. So you load it, import QP as CP. In fact, the goal of QP is to be a drop-in replacement for NumPy. So you could almost import QP as NP and just have all of your code run exactly as you would expect it with NumPy. So we're going to define a test routine where we generate a couple of big two-dimensional arrays, and then we multiply them together. And so in this case, these are 25 million element two-dimensional arrays. They're 5,000 by 5,000 on a side. So they're pretty big, not infinitely big, but pretty big. And to do this in NumPy, the generation and then the matrix multiplication takes about 3.5 seconds on our cluster. But we can do the exact same thing on the GPU, and we can see how fast the QP is able to do it. And amazingly, it takes basically no difference. In this case, we're still generating the random numbers in NumPy. We then have a statement where we move those arrays to the GPU. So the memory where these things are located is different. The NumPy arrays are generated and stored in memory that's the standard RAM of the CPU. In order for the GPU to actually process anything, we have to physically copy that over to the GPU. And so this is what the asArray function does. It takes some NumPy array and it copies it to an array on the GPU. So we do that, and then we do a matrix multiplication, the same matmul that we are used to thinking about. And instead of taking 3.5 seconds, it now takes 450 milliseconds. So it's a factor of 7 improvement with basically no complicated coding. Now this is, again, 3.5 seconds to half a second, who really cares? But if it's hours to minutes, that's a big difference. And for very, very little effort on the programmer's part. That's kind of a stupid, boring example. I am a big fan of the New York City taxicab data. For those that are not aware, the yellow cabs, and I think actually some of the other cabs as well, publish all of their data. So every taxi trip that's taken in New York, the start, the stop, the time, the mileage, the tip, the fare, all of that is published, which is wild. And so you can download, and there's a script in the repository to actually download. You can get it from this link as well. Each month of data comes as a CSV file, And they're all about a gigabyte in size. So they're relatively big. I have currently, I have a couple of months from 2017, but they have it, I think, going 5-10 years back. It's really an incredible data set. So we're going to play with some of these data right here. So we're going to use pandas, which again is this pretty friendly tool to read in the CSV files. So in this case, we have January and July of 2017. We're going to load in the first the first million rows in these files. This is not the whole month. Just for simplicity, I'm only doing 100 or a million rows from each January and July. And then we're going to extract from those data frames NumPy arrays for the tip and the distance traveled for both January and July. And this is just standard data frame manipulation, just using it as a way to read data. And we're going to move it to the GPU. And so just that same as array, we're going to bring the data over to the GPU, both for January and July. And I'm doing this because I'm thinking, wouldn't it be interesting to see is there a difference in pattern or in behavior between riders and how they tip when it's cold outside versus when it's hot outside? I have no idea. It just seems like it's an interesting question. So let's find out. So if we want to divide the tip from January by the distance, so this is kind of a tip efficiency, dollars per mile. We do this on a NumPy array. It takes 1.5 milliseconds to do this simple division. Whereas on the GPU, it takes 32 microseconds. So this is, again, a massive speed up for this. And this is a tiny amount of data. I'm just playing with it. But that's pretty nice. And again, when it makes the difference between something that can run over lunch or while you get a cup of coffee versus something that runs for hours or overnight, that's pretty powerful. And then because I thought it was an interesting example, we're going to actually take our tip efficiency and histogram it. So here we are, we start on the GPU, we then have to bring it off of the GPU memory so that we can be back into CPU memory where we can then plot it. And we do just a normal histogram of this tip per mile. And so in blue is January, and in orange is July. And we see that there is a small change, about a 4% difference. People are 4% more generous when it's cold out than when it's warm out and nice out. So, and the distributions are pretty interesting. So there's a clear peak. So this is a log scale. So this is the number of rides. And then this is the dollar per mile. And there's a peak at around 1. So people generally tip about $1 per mile. But the tail is somewhat different. And so as people, July, that tip falls off a little bit faster than it does in January, which I just think is interesting. So there's, in different ways of looking at the data, you can also pick out, there's certain trips that are a fixed distance, like from Manhattan to the airport to LaGuardia. And you see that as like a weird spike in the data. It's a fascinating data set. Definitely recommend anyone who's just a little bit bored or wants to take some interesting data and use it as a way to start using some of these tools. It's a fun one to do. So GPUs are really, I think, they are providing some new powerful ways to analyze data. They're only getting cheaper and they're only getting better. And these Python connections to GPUs with QP or PyCUDA or Rapids are really powering these explosions in machine learning and other computationally intensive tasks. And I can't recommend enough. The GPUs on the Commons partitions, both GPU and GPU devel, are free for people to use. Go use them, learn how to go with it, and see how you can use it to accelerate your work. So with that, there's a bunch of links here. This parallel programming, parallel processing is a huge topic. I've barely scratched the surface here. There are a bunch of different tutorials that are kind of at the intro, the advanced, and then also a bunch of these GPU parallelism that I recommend. And with that, thank you all, and I can answer some questions and stick around for a while. But thank you all so much for coming. And as Christine mentioned, these slides are available on our docs page. And we'll send out the YouTube video tomorrow, but please take a second to fill out the survey that Christine just posted, and take a look at upcoming trainings that we have for the next month. So thank you all very much. Have a good day.